This is an introduction to smoothing, one of the techniques that we will be using in our class. Smoothing is a simple technique. It's a workhorse technique used in about 60%, 70% of the forecasting approaches in the business world, primarily because it's quite simple, and for a little bit of data, short-term forecasting, 12, 14 months into the future, those time frames, simple single product, it can be very effective. There are three types of smoothing techniques that we're going to look at: single exponential smoothing, double exponential smoothing, oftentimes called Holt's smoothing, and then Winter's exponential smoothing. Understanding the proper use of smoothing techniques really requires us to have a pretty good understanding of the data that we're looking at. This is called Pagel's classification system, and it's taken from Barry Keating's book. If you look across the top, what we have is data in which there's no seasonality as a possibility, additive seasonality, or multiplicative seasonality. Down across the left-hand side, what we see is no trend in the data, an additive trend, an exponential trend, or a damped trend. Those are the three possibilities. So let's see how we would use this, for example. Take a look at our no trend effect and no seasonality. As you can see, I'm pointing to it right there. This is basically flat data. Okay, additive seasonality, notice the spikes for the seasonal parts here, here, and here are exactly the same height. And then multiplicative seasonality, notice the spikes for the seasonal part getting bigger. Single exponential smoothing is most appropriate for data that has no seasonality and no trend effect. Double exponential smoothing, or Holt's method, is most appropriate for data that has what we call, if you look here, level and then a trend, but no seasonality, either additive or multiplicative. And then finally, our Holt-Winters is an approach that we can use in which, notice, we have both a trend, we have additive or multiplicative seasonality. So exponential smoothing is widely used. It's easy to calculate. Limited amount of data is required. It generally produces accurate results. It assumes random variation around a stable level, and it can be expanded to include multiple methods in terms of seasonality, additive or multiplicative, or different types of trend. And notice this idea of Winter's method that I'm showing you here. That's when we add in seasonality. Now, the smoothing parameters, and I'll show you what those are in a second. The idea is quite simple. I want to select these parameters here to be able to produce the smallest amount of error in my forecast. So now, in terms of looking how single exponential smoothing works, let's go through it. Y hat would be my forecast. This is the actual amount of data that I have, not amount, but the data I have in the most recent time period. So let's say this is January of 2014. So this is my company sales for January of 2014. This is the forecast I had a month ago for January 2014. And notice now, do you see here, this is our smoothing constant. Okay, it's the smoothing constant, ranges between 1 and 0. Okay, so the idea then, in terms of single exponential, double, or Winter's method, is to produce a forecast by selecting this smoothing constant here that minimizes the amount of error in our in-sample forecasting. Moving averages, which we have looked at already, assign equal weights. When we did decomposition, assigns equal weights to the periods involved, the data, but exponential smoothing does not. So the way exponential smoothing works is it assigns declining weights AT is the last actual value that you have. So if I picked a value, a smoothing constant of 0.1, then the weight would be here. If I picked a smoothing constant for t minus 1 period, the weight would be this. And again, you can see the weights decline throughout all of the data you have in the history of your data, but they all sum to equal. So notice now the weights are not the same, whereas in moving averages, they would have been the same. If we take a look at a higher weight, 0.9, notice they also decline, but notice how very rapidly they decline. Single exponential smoothing then essentially can be looked at another way. We can use this as my last actual data. This would be my last actual forecasted piece of information, and then this would be the error here. So that's just simply another way of looking at smoothing. Now, single exponential smoothing rule of thumb. The closer the smoothing constant is to 1, okay, alpha, the more strongly the forecast depends on recent values. The smaller the smoothing constant, the closer it gets to 0, 0.1, 0.01, or whatever, the more it places value on older values. Historically, over the years, we have found that smoothing constants in single exponential smoothing of 0.05 to 0.3 work very well. Smoothing constants greater than 0.3 usually indicate that some other forecasting technique might be more appropriate. Now, let's look at the pros and cons. Pros, the positive part of it requires a limited amount of data. They're relatively simple compared to other techniques. They're expandable to include trend and seasonality. The problem is that, particularly with simple, that the actual forecast lags behind the data, and we really don't have any ability to adjust very quickly as the trend changes. Now, smoothing can be easily done in both Minitab and Excel. In Excel, it's called single exponential smoothing, and in Minitab, it's called single exponential smoothing. In Minitab, it's easy because there is a routine when you click stat and then time series and then single exponential smoothing. It will give you an opportunity to simply click optimize and let Minitab select the smoothing constant for you. The thing to remember about smoothing techniques, all right, is that there is no intuition. There's no rationalizing. There's no common sense to the model. We are essentially trying to pick a smoothing constant. So going back to our equation, we are trying to pick a smoothing constant here that simply minimizes the error, therefore giving us a good forecast ahead. So that's an introduction to simple exponential smoothing. Next time we'll look at double, and then we'll look at Winter's method.